So let's do like a little. Okay, let's do something. Let's summarize it. So this is the spectrum, okay, of any graph, linear graph, you know. So the bad graphs are those that their omega is like 1 or approaching 1. That's not good. Even omega 2 approaching 1 is amazing. Okay. Okay.
This is like the beauty contest of graphs.
Exactly. Oh, that sounds.
Because only
The regular graphs. Now, like scales, because it's not fair to compare like a D with a 2D. So a graph is called an expander, like in a like without referring to a parameter, if omega is bounded away from it. Okay? But omega, so both omega 2 and omega n are bounded away from one. We just want them not to be. And when I say bounded away, I mean, sorry, I should have said that. As a computer scientist, I never care about a graph. I care about a family of graphs. One per input size or something, one per size, or maybe we'll have sizes of not exactly for every integer, but infinite family of graphs. And when and all of them should have the same degree. And now what I'm saying makes sense. I want the omegas of this graph to be bounded away from one. For example, this graph, if I take the hypercube of increasing sizes, it's not bounded away from one. Close to one. The better rate than the cycle, but still. I mean, the degree is much higher. You would expect more than such a graph, right? So an expander is anything. So when I say an expander without referring to something, I mean anything for which omega is bounded away from one. When I think of a family of graphs, it's a one-sided expander if omega 2 is bounded away. Never mind that. And the best expanders we know actually can achieve this. Thing. So this is the winner. Right? So illusion is the most beautiful.
In the Galgador.
Galgador, here, minus this.
so the best expanders can actually reach the theoretical limit.
Yes,
That's really good.
that's it. I agree. And there are two proofs for that, like the group theoretic and the analytic one. And both of them are really, really nice. I'm giving a course about the other one next semester. Good, but anything here, as long as you're not approaching one, is a good expansion. Now, as I told you, there are such graphs. These come from Kelly graphs of non-abelian groups. You can actually show that with a constant degree, an abelian group cannot give you a good expansion. So if you are insisting on a constant degree and you want to construct a Kelly graph, it won't be a good expansion. It's nothing, just because they are abelian property. In fact, but still, if the degree is at least log n, log n, you can actually get very good expanders, very good Kelly graphs. So again, the degree is not constant, so it's a kind of different ballgame here. I'm not fixing the degree and asking for. But still, if the degree is like log n compared to the size n graph, it's still something which we use a lot.
And this is, for example, like has that the degree is low.
Right, but that's a bad graph. But you can tweak that, and it's actually related to, and we'll talk about it, to small bias sets, which we'll talk next time. Someone.
What if you take this with the cell groups?
No, set groups only half, because they add one. So if you add set groups to every element, they add one to all the eigenvalues. They also add the degree, but they add one to all the eigenvalues. So you actually want something that can do this, not that.
What about partial cell groups? Like
Some
placing a half there, so you have a random walk, but
it's called a lazy random walk sometimes or something.
something.
Stay there, right?
Yeah, but you stay at a lower probability than any statistic move.
So what people do, I'm not sure how that would behave. I'm just not sure. What we will do is we'll take the same group, but take different set of generators. That's going to be called a small bias set. We'll come from it from a different direction. It will be equivalent to that. And that in turn related to codes. So you told that if you have a code, a linear code, and you take right, a linear code have some vectors that span it. So, right, the dimension of the vectors is more than the number of vectors, because the span should not contain everything, should be some points in between. Now transpose this, like take the columns of those, so you have more columns than rows. This would be a good set of generators. So the way, so codes are very much related to Cayley graphs of those. Essentially, but we'll do that. That's something to do. And as to what I said, a billion groups can give you, so in this case, for example, you have at least n, or you have more than n. Once the degree is more than logarithmic, actually, Cayley graphs over a billion groups are good. They do great stuff. But if you insist on constant degree, they are not suitable. Okay. So then came this question of can you construct expanded graphs like in a like for every degree that you can work, like change stuff in the construction and play with it and argue not just about expansion. And so the zigzag construction that we use a follow, so which will start now, gives you something like here. So the zigzag will give you for any degree and any number of vertices essentially. So this will be like not d over, not square root of d over d, but something like something of that. I just want it just so that you can compare something like that. So it gives you something which is, you know, it's actually get better and better as d goes. It's good, it's not just constant. It's even better as d goes, but it doesn't quite get the half in the exponent that you have here. It's like a 1 over d to the quarter. So I don't know how impressive you think it is, but it is. Because to get that, I mean, you like, and that's a construction that like humans can understand and play with, and it gives something really good, really good. So let's start talking about that construction. I should say that there are ways to improve that using the same techniques to get something which is really close to that. So that's a paper by Amnon Tashma from our department and Avi Ben Arroyal, which gives what they call some quantum. So they got all of that. So they got like, so you want 1 over square root of d more or less. Well, there's the 2, but I'm going to be way off in the house of the 2 over brother times something which I don't know if you want to see, but it's like something like that. So it's like 1 over d to the half plus little over 1. So it's almost 1 over square root of d. This is much smaller than d to a power. It's literally 1 over log square root of d. This is smaller than here you pay like a d quarter price. Here you pay something. This is like d to the little of 1. So it's almost Ramanujan in that sense. But it's also more complicated, and it uses Cayley graphs. So it uses both Cayley graphs and that zigzag kind of idea all combined. We won't do that in this course. I did in the previous one. So. Questions? Shooting for this one. We'll just start. We'll just do the beginning of this.
Next semester?
No. Next semester we'll do this. We skip just all of them. Right. Okay, let's switch to the other topic. So today, what I want to get to is the explicit construction of expanders, which we get as the d to the 3 quarters we talked about, but we have to go through a little bit of work. The idea of the construction is to have like 3 operations. You start with a small graph and you apply these operations in a certain way. Each of them does something good and something bad. Some of them increases the size of the graph, which is good because you start with a small graph, but it hurts the expansion and also the degree. There's another operation that will decrease the degree, but will hurt the expansion. And then there's another operation, the best one, that decreases the degree. That's what I said, and slightly hurting the expansion. So these 3 together will allow us to construct the expander. You'll see. But the idea is like very computer science kind of construct, do things, rather than take a group and voila, everything's fine. It's quite different. And that's why it's amendable to changes, because you can do, you did things, you can insert your ideas into that. Oh yeah, let's start. And let's start first by me trying to tell you a little bit more about how we represent graphs, because we will need to be more careful. So far, a graph was just, whatever, you can represent it as a matrix or just write it down, but we will need something more committing. So if we have undirected graphs, we'll say that the graph is labeled if every vertex, so it's a d-regular graph, it labels its neighbors by numbers up to d. Okay, just says, this edge going out of me is 1, and so forth, this edge is b. They don't have to be consistent. So this vertex doesn't have to call this edge 3 as well. We'll call it 5. That's fine. Okay, it's really nothing happening. I'm just giving you more information. I'm just telling you which is the first, second, and so forth, like neighbors. And just a reminder, a graph is called weakly explicit if I can generate it in time proportional or polynomial to the graph size. And it's strongly explicit if I can actually do more. Given a vertex and a neighbor number, I can give you the corresponding vertex, that ith neighbor. So we are going to construct strongly explicit expanders. And we'll have 3 operations. The first one is the easiest one, is squaring. Okay, so we know that squaring just take omega to omega squared, right? Because all the eigenvalues are just squared. So and the absolute value don't change because it's square, so it's just square. But let me be more precise about what is squaring. So if you have an undirected graph that is d-regular, then the square of the graph G, which we do not by G squared, is actually defined as follows with respect to the labelings mentioned. So you give me a vertex name, not a vertex name, a neighbor's name. So it's just it should be a number between 1 and d squared, because the degree is d squared when you square a graph. But let's call it I, j. Let's denote our neighbors using 2 coordinates, I and j. And the ijth neighbor of a vertex u is the jth neighbor of the ith neighbor of the vertex. So say this is a v. So the ijth neighbor of g squared, to get to it, you go to the ith neighbor. How did that?
I should try to double click yourself.
עשה שידור לא חוקי. I did something illegal.
Because it switched to neighbors vertices.
Divide by 0.
First illegal action. So nerdy, the first illegal action. So the ijth neighbor of V in G squared is you go to the ith neighbor of V in G, and from there you go to the jth neighbor of where we got to at G, and so W is the ijth neighbor of V.
What about the D vertices that where
Good.
W is?
Right, exactly. So know that you have a lot of self loops in the square, because if you take I, like the diagonals, you always go over. So you have self loops in these constructions. You can slightly improve them if you remove them, but
Also, I have
D
like,
squared minus.
if you have 2 paths to W.
right. That's also so that will give you like self loops, parallel edges.
Yeah, so it's gonna the value in the matrix would be
2.
more.
Oh, yeah, exactly. And what nice about these labels is you actually encode more information, so you don't have to worry about it. So you can produce the matrix from that, but you can't really produce that from the matrix. It depends on you can have. So this is actually saying we are storing more information about the graph, right? Because now if there is an I prime J prime, then in the adjacent matrix I'll see a 2 or something. But here I actually in this function of labeling I actually have more information.
So I want to ask, why do we give the numbers? Don't we just look at all
Right.
the
all the neighbors, and that's it.
All the neighbors of my neighbors, let's
Right.
call that the graph.
So the sad news is that the reason is that we are going to have expander on the labels of the edges. We are going to take a big expander and a smaller expander on the edges leaving a neighbor. And so we have to give them names so that we can kind of match things up.
Those are gonna be your vertices? The edges are gonna be
Yeah.
your vertices?
And we are going to have edge between them. Edges between edges. Yes. So that's why maybe I can say something a little bit about it. If you take a square, if you take a square of a graph, then from the perspective of a single vertex, like this is a vertex, it happening in G, degree 5, this is in G. In G square, what will happen is that everyone will snob him, all of his neighbors, and will combine together, right? So we'll have a click here, not touching. Always do that. I'm pushing the wrong button. We'll have a click here. I don't know how to do it. Not touching this one. There's this one.
Left to the, yeah.
Not touching that because in the square what will happen is because of his existence, these and that, these two vertices will be connected. So through him they will meet. It's like you are friends and they meet through you and then they don't talk to you. So that's what and they're also going to talk to themselves because but the point is that squaring really what it does from the point of view of a vertex is putting instead of a star, a click. That's the star graph, which is this. You get a click. And squaring is going to be expensive for us. So essentially what we will do, we won't do exactly that, but essentially what we'll do, we will replace this click with an expander. Because if click are kind of close to expanders, but expanders are cheaper, the degree is smaller, then the hope is that if I won't take the exact square, but I'll take a square in the sense that I'll transform a star to an expander rather than to a click, maybe that will give me all the benefits of a square without paying for the square. So that's essentially what's going on. And that's why I need names for the edges.
It's like a succinct representation.
Right. It's in this context, people call it a sparse representation, sparse approximation of the click or the square. Exactly. But we are ahead of ourselves. I'm just
It's like a reduction, like going from we want to approximate the click on n.
right. So we do it for small.
We do it for d vertices instead.
Yes. And the point is it gives you like better expansion locally. Like G squared is a great expander locally because you have clicks everywhere, and you reduce. So you do it in a sparser way, paying much less, and then you kind of keep going. But again, we are ahead of ourselves. So the obvious thing about the square, but that we know already, is that the adjacency symmetrics of the squared graph, definitely if we define it with these labels, right, is the square of the original adjacency matrix of G, and also the random walk matrices. In particular, it means that this was there from before. Right? This is the new addition. Particularly, it means that omega of G squared is omega of G squared. So you see, it's a better expander.
Why?
Because all the eigenvalues are getting a square.
Oh. Okay.
And the absolute value is fine. I mean, there is not,
But
Yeah,
the
okay.
degrees are the same.
right. Good.
It's not
Good. Yeah, that's exactly right. So omega G squared is smaller than omega G, unless omega G was 1, which is a weird thing. It's smaller, so you are happy, you get a better spectral expander. But the degree is squared also. So like it feels like you gain nothing, and in fact, if you look at it carefully, you lost something.
no, I mean that omega of G squared is not omega of G squared because
No, it is. Because it's normalized, right? So, and the degree is also squared. So what I mean is that the omega,
okay.
like everything is normalized. But this like, yeah. So the point though is it's not worth your while to square the degree for the purpose of squaring the omega. You want to square omega or close to square the omega without squaring the degree. And that's what the zigzag is doing. More or less. Okay, so I don't think it's a good idea to look at the second operation. So let me just tell you in a high level. No, that's also easy, but let me tell you in the high level what we'll do. We are going to start with a small graph. You take even the complete graph and the vertices, if some loops or something. So something that we know is a good expander, but it's small. We want to produce infinite many things. So what we'll do is we're going to have a way which produces a graph which has a square number of vertices in the order. So from D you go to D squared. That's called tensoring. We will see what that is, but that increases the size. We will say D squared. But the problem is that it also increases the degree and it doesn't change the omega. That's good. It doesn't make whole, but it increases the degree. So you want a way to decrease the degree without hurting too much omega, because now the degree increased. Trust me. So that's going to be the key thing. It's called the zigzag. The zigzag is a way to decrease the degree without increasing omega so much. It's a weird thing. How can you decrease the degree of the graph? You have a graph. You're not going to take out edges or something. So that's a good thing. That's going to decrease degree. But it's going to hurt. So increase omega a little bit. And then you will have to, so you got this. So then you're going to have another operation, which is just squaring. Square is nothing. Is that so it increases the degree, but it improves omega. That. So that increases the degree, but omega is squared. And it turns out that overall in one iteration like that, you ended up with a graph which is of square size, has the same omega, or slightly even better, and the same degree. So you keep the degree and omega intact. Turns out that the losses are not as the losses as the gains. So you keep the degree and the omega intact and increase the size of the graph by square.
Wait, isn't the differential of the is just like x1 transpose times x2?
No, it's the tensor thingy?
Yeah.
No, it's a linear product. So this is a bigger vector.
It's matrix. The matrix.
No, it's a vector. So we'll talk about it next time. So here in the definition that I'm not talking about, we'll define the tensor between vectors, which will give you a big vector.
And it's just a matrix because it has two indices.
No, it's a vector. I mean, you can write it as a matrix, but it's not a matrix. I mean, you don't want to think of it as a matrix. You'll also do it to matrices. You take two matrices and take their tensor, and you get a big matrix like that. Okay, so anyhow, what we'll do next time is we'll show that all of this, it's not so long, it's like 2 hours. We show that all of these three operations like play nice with each other. The gains are higher than the payoffs. The payoff is good, right? The payoff is better than the payment or something. And so it's worth doing it like any number of times to get larger and larger expanded with the same amount. And that you can imagine you can play with, right? I mean, if you have this operation, you can add stuff to it to get more properties if you want. Okay, so that's next time. Really, next week I'm not sure exactly what we're doing. It's because of the war.
Yeah.
Yes. So I emailed like the people that are not here. I guess they are not here. What they want to do. I didn't get like a clear response, so I think I'm just going to repeat the difficult parts using examples also, new examples, but not moving forward, just like talking about what we did. But giving you examples, not just repeating myself. Once I think let's go for a while. Okay, see you next week.